Hello, everyone. Welcome back to our monthly global flood clusters monthly meeting with our keynote speakers. So this initiative formed a while ago, around 1.5 years ago, by the GeoX Global Hydroclimate Panel with the push from Peter. And we started working on this initiative. We had a kind of global flood workshop online. We brought a lot of kind of leaders across the globe to share their knowledge. They funded project related to flooding. And then we started this initiative from last January, and then I'm so glad to we have great presenter so far. Gabriele is one of them. They had Professor Paul Bates and a couple other great leaders and great scientists in water and flood-related research. So I would encourage you to look at their presentations and the discussion on GeoX YouTube channel. I will send the link after a while. And then also, I am pleased to inform you all that our proposal was approved by the GHP panel. So we are officially in, and then we can get this initiative going. And then at the end, we will conclude this initiative with the keynote speaker, with the steering committee that we have for this initiative. And then we submit our report to GeoX GHP panel for review. All right. So for this month, we have Professor Gabriele Villarini from Princeton University as our keynote speaker. Thank you, Gabriele, for accepting our invitations. And then the floor is yours. If you could share your screen and then
yeah, I'll be happy to.
Thank you.
All right, let's see. All right, just bear with me for a second. Doesn't matter how many times we use Zoom, there's always something. All right, so now I'm gonna swap screens. I assume you can now see my screen. Perfect. All right, so Via, thank you so much for having me here. Thank you all for the invitation. I will be sharing some of the work that we've been doing recently. I want to clarify right at the onset. You'll see my name as the one as the presenter. The reality is that the work, none of it would have happened or would happen without all the people in our research group and collaborators. And so instead of having a huge list of names right up front, what I have is wherever research is taken by ongoing or past projects, you'll see the reference at the bottom of the slide. And so that's my way of acknowledging the fact that the people who have been involved in this. And given the focus, or my understanding of the focus of the group, I'm going to tell you a little bit about floods and the relation with climate change at the global scale. Hopefully, this is something you'll find interesting and relevant. Some of the work has been published. Some of the work is in development. So some things are going to be clearer and crisper than others. But the one thing that in my mind connects all of these topics is the fact that for me, these are flooding and extreme events broadly intended is something that is personal to me. Some of you might know that I did my PhD at the University of Iowa, and more so, I did it at the time of a major flood in 2008 that impacted about impacted a large part of the eastern part of the state. And the figure on the top, the image on the top, is an image of the. Hold on one second. Oh, perfect. No. Wrong. Okay, good. It's an image of the University of Iowa campus. This is this building here is where my office was. You'll see that large part of campus were inundated, and this happened right as I was getting ready to defend my my PhD. Then in 2011, I was in Princeton doing my postdoc, and we had Hurricane Irene that caused a lot of damage, flooded roads, loss of power. And so these kind of events are the ones that have been shaping my current research interest. In particular, I've been asking myself, what are the drivers that led to this event, to these exceptional events? What does it mean moving forward? Is this a glimpse into a new norm, or is it something that is a major outlier? And also, can we predict these events? And the prediction, or can we say something about the future? And the future could be across a number of temporal scale, from short-term forecasting to long-term projections and everything in between. And so those are some of the guiding principles or some of the questions that I've been asking myself, and some of the research we've been doing in our group. So without any further ado, I'm going to jump right into it. And I've structured the presentation in three main parts. Part one and part two are the ones that are going to take the longest. And so the first part is thinking about processes. How do we get to where we are? Can we come up with models that can help us reproduce the year-to-year variability in flood peaks? And can we take the insights that we have gained from this analysis of the historical past to say something about the future? And finally, can we say something about how flood is expected to respond to difference in forcing? So these are the three main blocks that I will be discussing today. So let me try and bring everybody to the same, a little bit to the same plane. And what you see here is what I've done. I've taken a time series of annual maxima. So every year we look at the largest event. We can plot it as a time series. We can pull all the values together. If we want to be a little bit more sophisticated, we do some detection of non-stationarities in the record. Otherwise, we perform standard flood frequency analysis. In this case specifically, there is really no trend. And so in this case, we would assume, we would say that stationarity, we can't reject the hypothesis of stationarity. Hence, the future, we expect it to look something like the past, with the idea of stationarity, that what we experienced before is going to manifest itself moving forward. Of course, there are, we can think of it through different characteristics of the distributions, but that's the basic premise. And so this is what we would do if we were to use this data for design of future infrastructure. We would use the knowledge that we have from the past and design new infrastructure based on that. The reality is that we could encounter situations where things didn't change up until we had data, but then things started to change into the future. And given that we don't design for the past, but we design for the future, how do we incorporate these potential changes in flooding beyond just extending a trend line or assuming that the future will be the same as the past? Conrad Wasco and others looked at, it was a really nice assessment of where different countries are on how to incorporate change in the design of future infrastructure. There were several pages of tables similar to this one. This is just an excerpt. Many countries in the world, they have guidelines, not all of them, but And we can discuss whether the approach that the country is using is appropriate, what are the limits, what are the strengths, the weaknesses, but at least there is some kind of a guideline that practitioners can follow on how to incorporate change into the future design. When we look at the US, on the other hand, we rely on the Bulletin 17C, and this came out just a few years ago now. And when you look at these guidelines, what you see is that it says the time invariance was assumed in the development of this guideline. So stationarity was the cornerstone of Bulletin 17C. And if if you suspect that non-stationarity might be present, you can use time varying parameters or do something else. So they leave it really open on how to incorporate change in for the future. And so that doesn't really help on how to account change and how do we design for the future. So I'm going to go back to the example I gave to one of the time series. And so in general, when we think about flat frequency analysis, what we do, we take all of the annual maxima. We can do some peak over threshold. Today, I'm going to focus on annual maxima. And what we do, we treat all of these observations as coming from a single population. The idea that all of the events came from a single generative process. The reality, though, is that if we start stratifying the data according to the seasons, and we can use the season as the unit, if we can use the season as the proxy for different flood generating mechanism, we can see that now we start getting some variability. In this case, most of the peaks tend to occur in the winter and in the spring. Peaks occurring in fall and summer are much, much rarer and much, much smaller. And so the idea of the kind of work we have been doing revolves around, in a sense, bringing back physical processes into the flat frequency analysis that we do. The idea is that for a while, we have been focusing so much on developing more complex, more precise, more sophisticated ways of estimating parameters of a distribution. And maybe we have steered away from thinking of the numbers that we're looking at through the lenses of events coming from a mixture of different generative mechanisms, different processes. And we can discuss whether the seasons are the right unit for this kind of work, whether we should use something that is more granular. By all means, I'm happy to have this conversation at the end. But the idea is that what we've been trying to do is to bring back a physical understanding of the processes into the flat frequency analysis that we do. And so instead of working on annual maximum time series, what we've done is we said, okay, let's see if we can model the daily maxima at the seasonal level, and then let's mix this different distribution to give us what the distribution of the annual maxima might look like. And so I'll come back to that. So here we have done, as you can see here, a number of studies looking at applying this approach to sites both across the US as well as globally. We start with a compilation of a number of daily data sets that are global. When I say global, there are, of course, gaps. As you can see from these maps, there are certain areas of the world that they tend to be sampled much more than others. But this is what was currently available. Catchments, they range from small to large. We didn't stratify according to catchment size. And even though I'm going to show you some of the maps that have a geographic connotation, much of the insights or much of the conclusions that we'll try to draw, they tend to focus more on the climate regions and climate types rather than just the geographically constrained locations. And so here we'll talk about tropical, arid, temperate, and cold regions. We also have some sites in polar regions, but the sample size is much smaller than for others. And the other thing we do, of course, when you start spanning, when you start doing analysis across hemispheres, across large domains, the idea of water year that we can use to identify the seasons is going to be different. And so rather than assuming an October 1st as the beginning of the water year everywhere in the world, we follow the approach that Conrad proposed a few years ago. And so we look at the water year that changes regionally. Of course, there is spatial structure in what we see, and you can see this from here. But just to give you a sense that when I talk about the different seasons, not the water year varies depending on where you are in the world. Just as background, the other thing, methodological element I want to highlight is that when we'll compare the modeling results with the observations, I'll talk about this skill score, SS. And so what the skill score is a quantity that has been used in forecast verification. And what we want is to quantify not just the correlation between, say, the median of the fitted distributions and the observations, but rather the correlation, the linear dependency around the one-to-one line. And so we want to quantify the degree of agreement, not in with respect to the one-to-one line. And so what we want is to compute a quantity that is reflective of that. And so this would be your coefficient of determination, which is your potential skill, the maximum skill you can have. And then we penalize this dependence with respect to conditional and unconditional biases. And these quantities, they give us, they quantify the shift with respect to the one-to-one line, as well as the rotation from a 45-degree angle. So throughout, in some of the slides, you'll see this SS, this skill score. Keep in mind that it's bounded above the maximum value of 1, which means perfect agreement. And the value of 0 points to performance that is the same as what you would get from climatology, so the average over the period of record, and anything below 0 means you're doing worse than climatology. So we're going to try and live in a world that is above a skill score that is positive. Now, when it comes to the modeling, what we've done is we started extremely simple. And so what we've done is we said, okay, my response variable is the seasonal maximum discharge. And so if you take the fall season, this is the time series that, this is the record that we want to model, not just the trend over time, not abrupt changes, but rather the relationship with physical quantities. In particular, what we do, we use the Bayesian average and seasonally average precipitation and temperature. So what I mean is that here we are not tracking the development of precipitation and temperature in space and time, but rather we boil down the 3D information, so how precip and temperature evolve over the basin and over the course of a season, to a single number. So this is probably the simplest approach I can come up with. And rather than using a combination of complex variables, we just use precipitation and temperature. And the reason is that if given my goal of using these to predict something about the future, quantities that are a coarse scale and longer term is probably something I can trust the global climate models more than expecting them to capture the granularity that comes with modeling more at the weather scale, precip and temperature. And so when we're looking at the fall season, we have a precipitation for the averaged over the fall. We have precipitation from the previous summer, and the same for temperature for the fall and temperature for the summer. And these are, we look at them as proxy for a number of different processes, where there is saturation of the basins going into the season, snow accumulation, snow melt. We use these as very simple models. and predictors. The reality is that we can always make this more complex than it is, but let's start simple. Let's see how well we can reproduce the record of interest, and then we can always complicate it later on. And what we do is for every season, we look at every possible combination. We use a gamma distribution because of the bounded zero that discharge has, and we look at every possible combination among predictors. And we select the model that has the lowest Schwarz-Bayesian criterion as a way of trading off between complexity and the goodness of fit. And we feed different models across different sites and for each of the four seasons. And so when you do this, what you end up is with something like this. This is for one of the sites we have modeled. The circles are the observations. And then what you see is that here we have statistical and we have probabilistic distributions. And so we have, if you follow the red line, which is the median of the model distribution, what you see is that it's able to capture the ups and downs in the observational record. The nice thing here is that we don't need to account for trends or breaks a priori. If those manifest themselves in the forcings, precip and temperature, and if they are relevant, they should be embedded or transferred into the modeling of the peak, seasonal peak discharge. And so these are the results at the seasonal level, but at the end of the day, we want to results at the over the course of the year. We want the annual maximum. And so what we do, we recognize that if you take a cross-section, what you get is for every year, you have a gamma distribution whose parameters depend on precipitation and temperature for that season in that year. So now I'm going to focus on that specific year and tell you a little bit about the way we do the mixing. And so these are the distribution I showed you before. And what we do is a simple Monte Carlo approach. We start drawing variates from each of these distributions. And we say, okay, out of these four numbers that I've drawn, which one is the largest? It's the winter time. All right, so then I'll put it away. I do another draw. In this case, the spring value is the largest that we have. Take that number, put it away. I repeat this 100,000 times to give me the empirical distribution coming from mixing four different gamma distributions. And so this is what we end up getting. Now on the left, I'm showing you the PDF. On the right, I have the survival function. And so as we would expect, fall and summer, they don't really contribute to the modeling of the annual maxima, which are reproduced by this dashed purple line. But the interesting thing is that now the bulk of the distribution is controlled by winter floods, while the tail of the distribution is controlled more by spring floods. And this approach enables us to capture those dependencies. The other thing that is very advantageous about this model is that I don't specify a priori how many, the mixing ratio among the different seasonal models. We let the data adjust itself. And so in the future where conditions are going to be different, this approach enables us to account for changes in the seasonality of floods, which, as I'll show you later today, later on, plays a major role in explaining some of the results that we observe. And so then what we have, this is the time series of the annual maximum. Again, the circles are the observations, and the distribution is not a distribution coming from fitting the annual maxima, but rather from mixing the four seasonal models. And you can see that this very simple model is able to capture well the ups and downs that we observe, the interannual variability in the observational record. Now, what we have done recently is, as we try to build more and more robust models, what we've done is split training. And so for every location and every season, we use 80% of the data for training, 20% for validation. And we do this randomly drawing years. So at first, we draw 80% of the data for training, 20% we use it for validation. We fit every possible model for every possible season, and we keep track of which model is selected. Then once we have selected the 4 seasonal model, we repeat steps 1 and 2 5,000 times. And at the end of the day, what we do, we validate these 5,000 models on the 20% of the data, and we assess how well we are able to reproduce the annual maxima. So this is the skill score that I mentioned before, between the median of the fitted distributions and the observations on the validation years. And we do this multiple times. And finally, what we do is, instead of selecting one set of predictors that is coming from one possible of the infinite number of combinations we can have, or large number of combinations we have, we select predictors that have been identified as relevant at about 70% of the previous iterations. And the idea is that we want to use this training and validation not just to assess how well the model performs, but also to see which are the predictors that tend to be selected more consistently, so that we can have a more robust model validation. And just to bring everything together, these are the results for the cases where we have a positive skill score at the annual maximum. Another validation criterion that we use is to make sure that we have the correct probabilistic coverage from our results. And so that's another metric that we use. And overall, these are all, they all have positive skill score. We have tried to be as demanding, harsh, whichever way you want to think about in terms of our validation criteria as we can think, because we want to have models that perform well into the future. And so you can see that we have a skill score that on median is about 0.3. There is some spatial variability, but there is also spatial consistency across the different sites, without a strong dependence on climate region, with the exception of the polar one. But keep in mind that the sites in polar regions are the ones that have the fewest samples, in our case, 61. So the other, now that we have this information, what we can do, we can start looking at predictors. I'm going to focus on the US for some of the analysis. And so in this case, we see that for the spring season, not surprisingly, precipitation plays the largest role, with temperature that plays a more regionally varying dependence. And we can look at this across all the different seasons. One of the things that I always had in mind as we were performing this analysis is that here these are predictors that have been selected through statistical selection. And we all know that correlation doesn't imply causation. And so what we've done is we've used the Bayesian, causal Bayesian networks as a way of quantifying the causal evidence between the selected predictors and the selected predictors in our model. And what we use the number of different scales to assess the strength of the evidence. And what you see is that actually precipitate, as we would have expected, there is very strong evidence as far as the role of precipitation, as well as for temperature. And we can clarify this if we look at the most important and second most important predictor from a causal perspective. There is especially coherent patterns, and the evidence that we have selected is so that it's at least substantial. And so we've been trying to ask ourselves questions about, okay, you have this model, how well does it perform? How insightful it is, and how strong of an evidence do you get And we'll keep on asking questions, challenging what we have found. Now, I'm going to change gear just for a minute, because right now we have identified predictors that we believe are important in describing the year-to-year variability in flat peaks across the world. Now, the question becomes, what we want to do is, instead of extending the trend line or lack thereof, what we want to see is, if I know what these drivers are in the future, can I say something about what future flat peaks might look like under different climate scenarios? And we looked at a combination of a large number of GCMs. What we did a very simple empirical quantile mapping to bring the GCM, the basin average and seasonally average quantities, to the same level as in the observations. We looked at 4 scenarios, from a more sustainability-oriented one to a higher emission, a more business as usual case. The nice thing of the approach that we have is that we don't need high-resolution models. We can use models that have coarse resolution, and we go up to about 250 kilometer pixel size. And we look at the historical period until the end of the 21st century. The way we do it is, the other nice element of this approach that I believe is important is that we don't have a deterministic estimate, but rather we have a full distribution. So if we want to quantify the value of, say, the 100-year event of the event with the 1% annual exceedance probability, we can do this for every year into the future. And so, as an example, I'm going to show you the results for the 100-year event. And so I'm comparing 30 years in the historical period, 85 to 2014. So I have 30 estimates of the 100-year event against the 30 estimates of the 100-year event into the future, 2071 to 2100, for one of these scenarios. And so what we have a distribution of 30 values from the historical as well as for the future. What we want to examine is, do we detect shifts in the distributions of these extremes? And is this shift statistically significant or not? And if so, at how many sites? And so these are the results that we just got at the global scale. And so what we see is that there is a tendency towards increasing flat peaks and vast majority of the sites. These are analyses at the global scale. And this exacerbation tends to be higher for higher emission scenarios. But there is also variability across the different climate regions, with the temperate and the cold regions that tend to point to a larger change compared to, for instance, the arid regions. Now, one of the insights from this is that, in a sense, for those of you familiar with dry gets drier, wet gets wetter kind of paradigm, it seems to happen seems something like this happens also from a flat perspective, where you tend to get more sites showing change, whether in one direction or another, and this comes at the cost of the sites where we don't detect shifts, which is the middle panel. In a sense, we are, if we want to view this through the lenses of economics, we are losing the middle class. We are either getting richer or we're getting poorer, and this comes at the expense of what would be our middle class, and this is exacerbating more so as you go towards larger and larger, more extreme emission scenarios. The other element that I want to mention is, when we look at trends over the historical period, we see a mix of increasing, decreasing trends, but in many locations we don't detect changes. And oftentimes we use this evidence to say, when I'm looking into the future, I'm just going to rely on the past, and I didn't detect a trend in the past. I assume that there is no trend in the future. But the reality is that this is not a careful assumption. This is something that can lead to issues here, and it depends a lot on the different scenario you're looking at. As you go from more of a sustainability-oriented to a higher emission scenario, you see how either the gray dots, the sites where we don't detect changes, tend to either increase, or actually we see more of a change of signal of change. And the idea is that sometimes we tend to confound the absence of evidence with evidence of absence as a way of guiding design principles. And what I'm trying to stress is that just because we didn't detect changes in the past, we can't use it as evidence to detect for lack of changes in the future. Now, why do we see these changes? As I mentioned, seasonality plays a major role. And what we found is that as you go compared to the historical period, there is a shift in the seasonality of floods. In particular, you tend to go from more of a summer season floods to an earlier season, could be the spring, and even more so into the winter time. And some of this is driven to either changes in the circulation, changes in the storm track, earlier snow melt, increase in temperature leading to snow melt, transition from solid to liquid precipitation earlier on in the winter, more arid and drier conditions in the summer. And we see this across different zones. And so the idea is, and this is one of the advantages that this model provided us. Now I'm coming up with my time, but the last thing I want to show you is some of the most recent results we've been getting, which is instead of just looking at future projection, due to the simplicity and the parsimony of these models, we can also look at changes in different forcings. This is a study that was published a couple of weeks ago, where we actually look at the role of major volcanic eruptions on flooding at the global scale. Here we focused on 3 volcanic eruptions: Santa Maria, Agung, and Pinatubo. And what we did, and they have all different characteristics. Santa Maria and Agung, they tend to be more of an asymmetric aerosol plume, which tend to be concentrated in the hemisphere in which the eruption happens. So for Santa Maria, it's the northern hemisphere. For Agung, it's the southern hemisphere, while Pinatubo had a more symmetric aerosol plume. And so when we think about volcanic eruption, a lot of the interest and a lot of the analysis has been on the role of these aerosols in changing global temperatures. But much less was known about the impact on floods, given that the basin integrates a number of different signals. And so what we found is actually that for asymmetric volcanic eruption, what we see is a decrease in the peak discharge in the hemisphere in which the eruption happened. So in Santa Maria, when we look at tropical region, we see a reduction in flood peaks in the northern hemisphere, while the opposite happens in the southern hemisphere, where we see an increase. And this has to do, one of the physical reasons is shifts in the ITCC, in the intertropical convergence zone, for these asymmetric plumes. For Pinatubo, which was more of a symmetric aerosol plume, arid regions tend to show, basins in arid regions tend to show an increase compared to, say, the tropical regions where it was more of a decrease. And there is a different physical mechanism that we believe is at play here. And the other element we looked at is how long the volcanic signature persists, and we found it's for about 2 to 3 years, and then the signal dies down. The other work we have looked at is we have tried to isolate the role of the aerosols, the role of CO2 on flood frequency, on flooding at the global scale. And so here, what we have is on each row there is the different climate zone. Each column is a climate zone. Each row is changes that are either towards increasing or decreasing. And on the x-axis, what you actually have is changes in aerosol in CO2 concentrations. Value 1 is for the pre-industrial run, so what happened before the Industrial Revolution, think of 1870s. But we had idealized experiments that enabled us to ask questions: how would flood change if we have a quarter of the greenhouse gases. And so this is to the left of the pre-industrial concentration, as well as what happens if we double, if we quadruple a CO2 concentration. What do we find? And so what we see is that as we go to more and more extreme CO2 concentration, we see a departure from conditions that we have experienced in Europe from the pre-industrial perspective. And these changes are actually driven by changes in the seasonality as well. And what we see is the shift as we go from lower concentration to higher concentration. We see this shift towards more cold season compared to the warmer season. So this earlier anticipation of the flood season. And we can also try to have a storytelling approach that says, okay, if I look at the current conditions, to what kind of scenarios do they align more closely? And what we found is that they tend to align more closely between pre-industrial and 2 times CO2 conditions. And if you think about where CO2 concentrations are with respect to the pre-industrial round, we are at about 1.5 times pre-industrial level. And so this kind of approach enables us to identify what is the most likely scenario in which we are, today's condition would resemble. So with this, I'm gonna wrap it up and summarize. And what we have done is we've developed very simple process-driven approaches that enable us to say something about changes in flooding at the global scale. We have found that flood peaks are projected to become more extreme, exacerbated with respect to the historical past. Just because we don't detect changes in the historical record, it doesn't mean we can use it as evidence to say that there are no changes moving forward. And finally, this simple model enables us to probe to ask different questions, to look at the role of different forces in isolation from others. So with this, I'm going to stop, and I'll be happy to take any questions. Thank you for your attention.
Great presentation, Gabriele.
Thank you.
Yes, great. So see everything comprehensively from different angles. Very nice.
I'm probably my own hardest critic in a sense. I always say, okay, I would ask if somebody, what about this or what about that? And so that's why we keep on trying to tie those loose ends, trying to convince ourselves that, again, these are models. But again, can I try and falsify what we have found more and more? And so this is work that has been happening over 5-10 years, actually. So the more we know, the more we can refine it and improve it.
Yeah, that's brilliant. Brilliant. Is there any question for Gabriele here?
I see Mohammed has his hand raised.
Yeah, thank you, Gabriele, for the presentation, and greetings from IO and IHR.
Hey,
thank you. My question is mostly regarding the forcing part of the climate models, and specifically, I'm wondering if there are good approaches to downscale those scenarios, either in deterministic or probabilistic way. And I would give you the contest is mostly for precipitation frequency. There are now efforts in the United States, basically led by NOAA, to come up with Atlas 15, the new precipitation frequency, I would say, database. And there is kind of limitation on how to deal with those forcing in terms of spatial and temporal resolution.
Yeah. So the answer is, I'll try to give you as straightforward as an answer as I can, but you can understand that this is, there are many nuances. And so I'm sure that there is something I'm going to trivialize, something that, but so the answer is yes, it can be done. we actually, in our group, we have been working on new IDF curves with a new statistical approach that is different from others that enable us to go from hourly to multi-day, all within the same modeling framework instead of fitting multiple temporal horizons. And so stay put, more will be coming out hopefully soon. But yeah, so of course you can do downscaling. I mean, we have done it. We have developed a large database as part of other projects. And we have done this from a flat frequency perspective. For instance, we have a few studies where we looked at the role of different downscaling techniques from a flat frequency perspective. We have work where we look at the role of reference data in the downscaling and how different results you get from different, depending on how you train your data compared to your downscaling errors. There is in the US, I'm sure you're familiar with LOCA2, which has been used for the National Climate Assessment for the latest report. It's daily. It's a 6 kilometer resolution, multiple scenario, multiple models. And so that would, and it's both for the past and for the future. So that would probably be the first thing I would look at without having to reinvent the wheel. To do downscaling across large domains, it's computationally expensive. The storage becomes an issue. We're talking about multiple terabytes, many terabytes of data. And so we are doing some of that. We use it to force hydrologic models. So we have been doing that kind of work. Here I was trying to take a different angle, given what trying to cater to a broader audience that is part of this group rather than something that is US-centric. I was trying to have more of a global perspective. And at this point, the statistical models, they work, they are, I don't have to worry about the resolution of the data. Whatever you give me, I'll end up coursing in it. So it doesn't matter what it is. So I would say, Mohammed, step one, I will look at LOCA2 if you haven't already, and then it all depends on what your goal is.
Thanks so much. Thank you.
Of course.
Yeah.
Say to folks at IHR, your background looks very familiar. So those walls.
Right. Okay. Any other question for Gabriele?
I have a question.
Yeah.
Josh.
Yes.
So, I was looking at your skill score map, right?
Mhm.
And over the US, it looks like sort of over the Ohio River Valley, sort of the eastern Midwest, it kind of does a little bit worse. And I was curious if you thought about maybe why that is. And going back to sort of what you said at the beginning, right? Your choice of 4 seasons. Have you thought about how you would make that more flexible across different locations? So maybe you only have 2 seasons and they're broken up in different spots. And
Yeah,
how to
so
improve the results.
Yeah, so and I'm looking at that. So these results, I got them 2 days ago. So we're still, in a sense, digested them. But what I would say is I'm not trying to chase perfection or increase skill. We have been asking from a quantitative perspective, people usually plot correlation coefficient. We have done it ourselves and use that as evidence. The reality is that here I'm trying to get with respect to the one-to-one line. So it's even more demanding. If I were to just show you the correlation coefficient, would actually be much higher than the skill score that you see there. And so, and even in terms of processes, drivers, stratification, the one question I always get is, why don't you use machine learning? That's one that is always, I get it. And the question is absolutely, or why didn't you use soil moisture as a predictor? Or why didn't you include groundwater? Or why didn't you include irrigation? And the question is like, absolutely legitimate question. The reality is that if I'm trying to project future changes in floods, do I believe that I can get soil moisture data that is relatively meaningful from GCMs? Do I believe that I have historical data for groundwater withdrawal or irrigation over decades? Can I use machine learning? Absolutely. But why do I need to? These are simple models that I can explain to practitioners. And my expectation is that by using machine learning, it would tell me something that maybe I should know just from first principles, thinking about what the important predictors are. And if I can come up with a simple model that gets me quite a bit ahead, I'm happy to do that. The other question sometimes is, what about using tropical cyclones or atmospheric rivers to stratify your population? Great questions, great point. The problem becomes, do I believe that the GCM with the 250 kilometer resolution is going to spin up meaningful tropical cyclones? No. And so I try to meet the GCMs where they are rather than thinking about what would be the most comprehensive approach. And so to your question, Josh, about splitting 2 seasons, different season, monthly model, that's why early on I said we can have a conversation about what's the most useful, most relevant, granular modeling or horizon development of models. But then at what price? What do I pay to have that increased flexibility? And so I'm a simple guy. I have 4 models, 4 seasons everywhere. You can think of even 12 models where you have a 3-month moving window where every month you develop a model that is representative of a 3-month period. And so you have the smoother transition. By all means, it's why one thing we looked at is why did we look at precip over the previous 3 months? Could it be that the memory of the system is longer? We did some sensitivity analysis we did with weighing the average. So the months that are closer to the season of interest gets a larger weight than the other ones. At the end of the day, it didn't really make a big difference. And so we can always make it more flexible, more complex. And people should do that. It's just that for what we are doing, I would say this was good enough. And it's good enough for the purpose we have, which is not to perfectly reproduce the idiosyncrasies and dynamics of precip and temperature at the basin scale, but to get to where we might extract useful information from the GCMs. And one of the things that, one of the lessons that we've learned is that it seems that it's more of the excursions from the average state of the basin, basin conditions that are driving the signal rather than the magnitude itself. And so the departures from average state for the principal temperature, they seem to be more dominant than the absolute values. And we're doing some other work here with Amilcare Porporato and one of his students, try to understand better the connection between the short-term events to this longer scale aggregation. And so again, try to learn more and more about what we're dealing with. Josh, it was a very long-winded answer. It was probably more than you bargained for, but this is what you get. This is,
Yeah,
and we're friends, so you can give me grace,
yeah,
right?
no, thanks. I think that was great, and I love the approach. I love the fact that you're doing this with very simple, like temperature, precipitation, because those are the things, you know, that we can
GCMs,
more reliably rely
Yeah.
on for GCMs.
And
So
there
I
are
think
more
that's great.
GCMs that give me those.
That's right, and we have that data, so I think that is a great approach. Yeah, and I think it would be interesting to just kind of understand within the framework of what you have, like why is that region doing worse? Is it like, you know, you said, is it the correlation? Is it the conditional bias or the unconditional bias? And, you know, what does that mean about the model? Like if maybe temperature and precipitation just aren't good enough in those regions. And then somebody who's in that region may say, hey, you might want to do something else or do something more if that's not what the skill level you're looking for.
Yeah, and this is so my thinking is that there is really no one model that works across the all scales. So that's why we've been developing new hydrologic models that enable us to get more at the granular level. So if this gives you that 20% that gets you 80% of the way, but if you need to to do something that is much more detailed. There are other ways. If you don't care about the next 100 years, then looking at other quantities is relevant. And again, this is just one answer, and it's not the answer. We are coming at this also from an hydrologic modeling perspective, and so we're going to have results soon across very large areas. And then we'll compare, if we're moving in the right direction from both approach and they're independent of each other, it gives me more confidence that we might be in the ballpark. And if not, why do we see these differences?
Yeah, I think it's great. Thanks.
Thank you.
Yeah, great. Thank you, Josh. Any quick question for Gabriele before we close? So I just want to comment one of your figure that you had for US for the Carolinas. So there is actually a kind of a very complex issue that we have in flooding between South Carolina and North Carolina. There's a catchment there. And then your result shows that increasing trend, which was really in good agreement with what we get there with flooding, It vanished actually two small towns there. So it's amazing me sometimes that how that statistical test can really tell us a lot about what's going on in the system. That's really interesting.
Yes. No, yeah. So there is nothing wrong with the simple. I mean, I always think there is beauty in simplicity. And so I don't, I'm a simple guy, so.
Great. Thank you very much, Gabriele, for sharing
Thank
your
you.
knowledge with us. It was really nice to have you. And thank
Thank
you all. I also put some information in the chat regarding the Google Doc where you can put your papers or project. If you're interested, we use it in our report that we submit to GeoXGHB. We ping you again, Gabriele, for be a part of this report so that you can put your study and your case study in the report for us. And then there are the website for the Global Flood Crosscut project. So next month, we will have Dr. Ben Livne from University of Colorado. Please join us on October 3rd, the same time. So I'm sure he is going to teach us a lot of good things about flooding as well. So again, thank you all for joining us. And I lead this initiative, by the way, by Josh, Dr. Josh Rondi and Dr. Conrad Vasco from University of Sydney. So hit us any email, any question that you have about this initiative, and then glad to have you all in our program. And please join us in next month. Thank you and have a great weekend. Thank you, Gabriele.
Everybody have a good weekend.
Take care. Thank you.